Thank you for the introduction. And first of all, I would like to thank the organizers for their really great efforts in organizing this wonderful scientific event, which gives us this nice possibility to meet together and to discuss our research in real space, not only virtually. Okay, and I also would like to thank Alexander for inviting me to this session, then I would like to, and first of all, I would like to present you my collaborators. They are Alexander Bobkov from Institute of Solid State Physics and Черноголовка, Mikhail Silayev from University of Uvascola, and Andrei Mazanik, who is a PhD student from Moscow Institute of Physics and Technology. Okay. In the beginning of the scientific part of my talk, I would like to explain you the main idea behind our work. It is very well known that condensate motion usually tends to break Cooper pairs by inducing their center of mass motion, which makes the momenta of two electrons to be not exactly opposite, and thus the condensate motion suppresses superconductivity. But I am going to talk about the superconductivity induced by the condensate motion. What does it mean? Well, we consider an SF hybrid system, and it is very well known and will be already discussed in detail by the previous speaker, which in such a system there are no superconducting correlations deep in the ferromagnet. They only penetrate into really small distances of the order of a few nanometers, if the condensate in this structure is at rest. But in this talk, I will tell you that if the condensate motion along the interface induced in such a structure, then the triplet superconducting correlations can appear deep in the ferromagnet at distances much larger than the short magnetic coherence length. That's the main idea of my presentation, and that's what I mean by saying that the condensate motion induces superconducting correlations. Okay, the outline of my talk is the following. First of all, I will give you some brief introduction about the mechanism of long-range triplet generations, known mechanisms, and then I'm going to the next part of my presentation and will describe the long-range triplet generation by the moving condensate. And first of all, I will explain you the basic mechanism, and then I'm going to give you two particular examples of the long-range triplet generation by moving condensates. The first one is the generation by Meissner currents, and the second one is the generation of dynamic long-range triplets by alternating electric fields. Okay, here is the introduction. As you already know, and as it has already been discussed in the previous talk, the triplet Cooper pair, their function is usually described in terms of the so-called D vector. Different components of the D vector correspond to different projections of the triplet wave function onto the quantization axis. The DZ component along the quantization axis describes opposite spin pairs corresponding to zero spin projection onto quantization axis, and dx and dy components of the D vector perpendicular to the quantization axis describe equal spin pairs corresponding to spin plus minus 1 projection onto the quantization axis. And the opposite spin pairs are short range in the ferromagnet, and their penetration depth is the order of the magnetic coherence length, which is typically short. And usual superconductors of like iron or permalloy, it is at most a few nanometers. But equal spin pairs are long range in the ferromagnet, and their coherence length is of the order of the normal state coherence length, which is typically much larger. It is very well known physics, which is described in several nice reviews. Of course, such equal spin pairs are highly desirable for superconducting spintronics. But if there is no anything special in the system, then in hybrid Ceph homogeneous ferromagnets, only opposite spin pairs are generated, and we need something special to generate equal spin pairs. Several mechanisms of their generation are known, and the first group of mechanisms is connected to its generation by a magnetic inhomogeneity. I will not deal with this group of mechanisms during my talk. It has nothing to do with physics I am going to discuss, but it was nicely discussed in the previous presentation. And the second group of mechanisms is connected to the long-range triplet generation by spin-orbit coupling, and I will discuss it in a little bit more detail because it is directly related to the topic of my talk. Okay, long-range generation by spin-orbit coupling was originally proposed by Sebastian Bergeret in the Liata Kotlim and the theoretical papers, actually this generation by spin-orbit coupling can be also divided into two groups. The first mechanism is connected to the precession of the spin of diffusively moving pairs in the presence of especially inhomogeneous triplet correlations. And the second mechanism is actually just anisotropic Dyakonov parallel spin relaxation. The both mechanisms were discussed in a number of theoretical papers, and there were theoretical proposals to generate long-range triplets due to geometric inhomogeneities of triplet correlations in different structures, and also in order to have the long-range triplet generation by this anisotropic Dyakonov parallel spin relaxation mechanism, you need a magnetization component in the ferromagnet to have a perpendicular to the interface component. Okay. All the discussed examples of the long-range triplet generation by spin-orbit coupling exploit intrinsic material features, geometric inhomogeneities, or manipulation by the magnetization. But it is obvious that it is highly desirable to have in hand a mechanism of external controllable switching on and off long-range triplets, and moving condensate provides a possibility of an easy control of long-range triplet. And first of all, I would like to explain you the basic basic mechanism of this generation. Let's consider the simplest structure, superconductor ferromagnet hybrid with a spin orbit coupled interface, which can be realized, for example, by putting a platinum layer between the superconductor and the ferromagnet. And if the magnetization of a ferromagnet is along the interface and has no perpendicular component, nothing happens in the system.
If 5 minutes.
Okay, if there are no, it's fine. As there is no moving condensate. And in order to explain the basic physics, let's consider this interface is a quasi two-dimensional superconductor with effective exchange field, and for Rashba type spin orbit coupling, we have two helical Fermi surfaces here. There is no unique quantization axis, but opposite moment electrons still have the same quantization axis, and pure opposite spin pairing is possible. But the situation changes if we apply an exchange field. There is no the unique quantization axis, and therefore the triplet order parameter, which d vector is perpendicular to the exchange field, appears. It corresponds to two equal spin pairs, but it's not enough for generation of long-range triplets in the ferromagnets, because this d vector is odd in momentum, and therefore it is totally suppressed in diffusive ferromagnets. But if we apply a condensate motion with the momentum component parallel to the exchange field, then according due to the Doppler shift of the quasi-particle spectrum, the amplitude of this d vector acquires a momentum-dependent component, and after the averaging over the impurities, it has purely isotropic equal spin component, which is now long range in the ferromagnet. This is the basic mechanism, and because I'm short of time, I will consider only one particular example of the long range triplet generation. It is generation by Meissner currents, and if we consider such a structure and there is no moving condensate, we have only opposite spin correlations. But if we apply a magnetic field perpendicular to the plane of our screen, equal spin pairs appear according to the mechanism described above, and if we compose two such structures into the Josephson junction, it will have, we predict, highly unusual interference patterns for such Josephson junctions. It can be considered to the standard Fraunhofer pattern. First of all, there is no Josephson effect at zero applied field, because there is no long-range triplets. But for small fields, long-range triplets appears, and the amplitude of the triplet correlations penetrated from the both interfaces are proportional to the condensate momentum. That is, they are proportional to the magnetic field, and the resulting current is proportional to the field squared at small fields. At larger fields, it should be multiplied by the standard Fraunhofer factor, and we end up with this interference pattern with linear in magnetic field envelope. Well, because my time is over, I should go to my conclusions. I should go to my conclusions, and I can conclude that moving superconducting condensate allows for externally controllable generation of long-range triplets and superconductor ferromagnet hybrid structures with spin-orbit interfaces. These long-range triplets manifest themselves in unusual dependencies of the interference patterns of the Josephson current, and they also allow for controllable by supercurrent zero pi transitions in SFS Josephson junctions. I can skip the dynamical superconductivity because I did not present it, and thank you for your attention.
Very interesting. So in view of time, I have short question. So to control pi junction, then you need kind of external injector, perhaps, yeah?
Well, yes. Okay.
Second point, yeah.
In order to have controllable zero pi junctions, the magnetic field triplets are not suitable. The point is the critical current is proportional to the product of vector condensate momenta at the both interfaces. And if the condensate motion is induced by the magnetic field, the condensate momenta at both interfaces are opposite. And now we have a pi junction. But if we somehow make them equal, at least in the same direction, when we will have zero junction. And therefore, in order to have a controllable zero pi transition, we need a setup like this. We need to generate this condensate motion by passing a supercurrent via, I don't know, some additional leads. And if they reverse the supercurrent direction in one of the leads, we can switch our junction between 0 and pi states.
Okay, yes, okay.